Today we are going to discuss 35th lecture of this course, which is on ground response analysis, and it is part of the 5th module of the course. And you may be aware that the 5th module of the course is on soil erosion interaction for deep foundations. So within that module, SSI for deep foundations, we have 6 chapters, and out of that, first 4 chapters has been already discussed. Today, we are going to talk about 5th chapters of the 5th module, that is ground response analysis, or in the short called GRA. In fact, GRA is the first step of any solution interaction analysis, SSI, and it is very important to know what is ground response analysis for earthquake resistant design of structures, foundations. So what is contents of the today's lectures? What we are going to talk is one-dimensional ground response analysis, two-dimensional, and boundary conditions. So within one-dimensional ground response analysis, let's talk about that. What is the importance of this? One of the most important and commonly encountered problems in geotechnical earthquake engineering is the evaluation of ground response, because it helps in many problems of the geotechnical earthquake engineering. And what are the problems? These are to predict ground motion, for development of design response spectrum, which is one of the important issues for design of structures, to evaluate dynamic stresses and strengths, for evaluation of liquefaction hazard, and to determine the earthquake-induced forces that can lead to instability of earth and earth-retaining structures. So that means the ground response analysis are useful for design response spectrum, liquefaction, as well as for design of the earth and earth-retaining structures, for example, retaining walls. Now coming to that, under ideal conditions, a complete ground response analysis would model the rupture mechanism at the source of an earthquake, the propagation of stress waves through the earth to the top of the bedrock beneath a particular site, and would then determine how the ground motion, surface motion is influenced by the soils that lie above the bedrock. So in ideal condition, this should happen, that we should model the rupture mechanism of the source itself. In reality, the mechanism of fault rupture is so complicated, and the nature of energy transmission between the source and the sites is so uncertain that this approach is not practical for common engineering applications. Approach means where you are modeling the rupture mechanism of the source of the earthquake along with that. So that is not possible. So what we do, we try to simplify the problem a little bit and continue with that. What we do in practice, there are some empirical methods which are based on the characteristics of recorded earthquakes, which are used to develop predictive relationships, and these are often used for what is called seismic hazard analysis to predict bedrock motion characteristics at the site. Now coming to the problem of ground response analysis, it is one of the determining the response of the soil deposit to the motion of the bedrock immediately beneath it. That means, suppose if you have a bedrock and the motion at the bedrock is given to you, then what will be the response of the soil layers and what will be the response of the ground surface? That is our objective in this lecture. Despite the fact that seismic waves may travel through the tens of kilometers of rock and often less than 100 meters of soil, the soil plays a very important role in determining the characteristics of the ground surface motion. So, the earthquake source is basically it's a focal point, and focal point is at a depth of in kilometers. Even if you consider a shallow depth earthquake, it could be 5 kilometers, 7 kilometers. In case of moderate earth, intermediate earthquakes, it could be more than 20 kilometers, or even focal depth in some cases maybe more than 100 kilometers. But when these waves are traveling from the focal point towards the ground surface of earthquake wave, they passes through the rocks for the kilometers, and the soil cover on the top of the rock is in few meters. Mostly it may be less than 100 meters, it could be 20 meters, sometimes even 10 meters or 5 meters only. So, but when the waves are traveling through the rock, their characteristic doesn't change much. However, when these same waves are passing through the soil, which is maybe in meters, then their characteristics changes much. So this is the objective of today's lecture, that how the soil influences the ground motion. So talking about this, the influence of local soil conditions on the nature of earthquake damage has been recognized for many years. And earlier, the seismologists and later geotechnical earthquake engineers have worked toward the development of quantitative methods for predicting the influence of local soil condition on strong ground motion. So objective is here that how the local soil conditions changes the strong ground motions. Over the years, a number of techniques have been developed for ground response analysis. And the techniques are often grouped according to the dimensionality of the problems that can be addressed. So when we talk about ground response analysis, GRA issue are deals whether you want to carry out one-dimensional analysis, two-dimensional analysis, or three-dimensional analysis. And naturally, if you want to carry one-dimensional analysis, that is more simple. And we will start from 1D ground response analysis before we discuss 2D ground response analysis. And we are going to talk in detail about 1D ground response analysis, how it can be calculated even without using some software for a simple case. So for this case, when a fault rupture below the Earth's surface, then body waves travel away from the source in all directions. We have already discussed that body waves means either P wave and S waves. As they reach boundaries between different geologic material, they are reflected and refracted. So when during the earthquake, what will happen? There will be rupture of the fault. And when there is a rupture of the fault, then the body waves will travel and they are traveling in all directions. Okay. And when they are traveling, then they encounter different geologic materials. And at the interface of two different materials, then there are reflection and refraction also. And since the wave propagation velocities of shallower materials are generally lower than the materials beneath them, because as you go deeper and deeper, it is expected that materials become hard or more stiff. So as a result, inclined rays that strike horizontal boundaries, which are coming from the down, are usually reflected to a more vertical direction. And by the time that these rays reach the ground surface, multiple reflections often bend them to a nearly vertical direction. So what you can see here. So this is the figure which is showing for 1D ground response analysis. And this analysis are based from the assumptions that all boundaries are horizontal and the response of soil deposit is predominantly caused by as such waves propagating vertically from the underlying bedrock. So what is here? You have fault here. There is source of earthquake, and the waves are traveling from here towards the ground surface. Initially, these waves are inclined waves. Okay? But when these waves come near to the surface, then they pass through the different geological and superficial layers, and their properties are different. So as a result, there will be reflection and refraction at the junction or at the interface of these layers, and they will bend these waves into vertical directions. And when these waves come to the at the base of the structure, then then it becomes almost vertical. So the refraction process producing nearly vertical waves propagation near ground surface. So this was the case. Here we assume for 1D one-dimensional ground response analysis that these waves consist of SH wave, which is, you know, the SH wave is nothing but shear wave with their particle motion is in the horizontal direction, and wave is propagating vertically upward. Okay, so with this condition we go ahead and let's define some terminology before we go ahead with the 1D ground response analysis. Here you could see in this figure, in the first case, you have free surface motion. That is nothing but the motion at the surface of soil deposit. So that means on the top of this surface there is nothing. Then you have bedrock motion, which is the motion at the base of the soil deposit or the top of the bedrock. Okay. Then third is called rock outcropping motion. Again, this is motion at a location where bedrock is exposed to the ground surface. So if here bedrock was down and on the top of bedrock you have soil deposit, but if it is exposed to the ground surface, no soil deposit, then it's called rock outcropping motion. But there could be a case when bedrock is not exposed to the ground, but it is deep, but there is no soil cover on top of it, then it's called bedrock outcropping motion. Okay. So normally, by the seismologist, most of the time, acceleration time history or ground motion is available at rock outcropping motion. And once it is rock outcropping motion, then this motion, recorded motion, will be free from the influence of the soil on the top of it. So we prefer that that motion or control motion given by the seismologist should be in the form of rod output motion here or here. Continue with that. Now for 1D analysis, we use what is called linear approach. That means for elastic approach. That means assuming that those behavior of soil is nonlinear. But if you do the nonlinear analysis, then it will be very complicated. So for this purpose of this course, let's consider linear approach. For this case, the transfer functions can be used to compute the response of single degree of freedom system for the ground response problem. Transfer functions can be used to express various response parameters such as displacement, velocity, acceleration, shear stress, and shear strain to an input motion parameter such as bedrock acceleration. So what you have, input parameter is given as in terms of acceleration times speed, but your output could be acceleration itself, or it could be displacement, velocity, or shear stress or shear strain, whatever one is interested in. Because this transfer function technique relies on the principle of superposition. This approach is limited to the analysis of linear systems. Nonlinear behavior can be approximated using what is called an iterative procedure with equivalent linear soil properties, for example, shape, program shape. Now, for continue with that, let's have the one case for 1D case. First thing, this is the easiest scenario to make you understand, is a uniform undamped soil on ridge rock. Though is real soil deposit will consist of a number of layers, but for time being, we are considering only a single layer on the top of a bedrock, and assuming that properties of this layer is constant throughout the same, that means it is basically homogeneous medium. Let's assume that thickness of this layer is h, and here, as you can see in this figure, that z is shown downward. That means z is positive downward. So z will be 0 at the ground surface, and the value of z will be h at the bedrock level. While u is the particle motion of the waves, which is traveling from down to up or up to down. Here, for simplicity, what we are assuming that this is an undamped soil layer. That means we are neglecting damping of the soil time being. So later we will consider the damping of the soil also. Okay, so continue with that. Uniform undamped soil on ridge rock is considered, and in this case, harmonic horizontal motion at the bedrock will produce vertically propagating shear waves in the overlying soil. So first of all, we are assuming that your input motion consists of only harmonic excitation, not real earthquake excitation. That means your input motion have constant frequency, and that frequency is given as omega as written here. So a harmonic excitation is considered, and as already said, that we assume the vertically propagating shear waves. Okay, so the resulting horizontal displacement can be expressed using the principle of wave propagation. First of all, this displacement u will be function of z and t, where z is the depth and t is the time. So as the time changes, it will change. As the depth changes, it will change. Now this displacement can be, because it will be coming from two components of waves. One is traveling upward, another is traveling downward, and both components have similar characteristic omega t plus kz, and another is omega t minus kz. What is omega? Omega is frequency of excitation, angular frequency. What is t? T is time, and z is depth. But what is k in this here? K is nothing but it is called wave number, and k can be defined as omega over bs. Okay, so in this equation, k is the wave number, and this wave number is written here, omega divided by bs, where bs is nothing but shear wave velocity of the medium, and a and b are the amplitudes of wave traveling in the upward and downward direction. Upward direction is negative here, and downward direction is considered positive, because z is considered positive in the downward direction. Now at the free surface, you have z equal to 0, and at z equal to 0, you can apply the boundary condition, and boundary condition that shear stress must vanish, and shear stress is nothing but del u by del z, multiply by E, that strain del U by, so that means when shear stress must vanish, that means shear strain must vanish. So once you say del U by del Z equal to 0, if you set that for any time t at Z equal to 0, then you get A equal to B, because you will get minus sign here once you differentiate with respect to Z, and then once you do, all other things will be same. So it will yield to you that A equal to B. Okay. Here, one thing I would like to point out: what is Vs? Vs is nothing but what is called Vs is called shear wave velocity, and we have already discussed many times that this shear wave velocity is nothing but it can be obtained if you know the shear modulus and mass density. So Vs is shear wave velocity, and as by this time you may be aware that this is nothing but G by rho. So the shear velocity can be calculated from this simple relation. Okay, so this is already discussed many times. Okay, now continue with that. So applying the boundary condition A equal to B in this equation can be simplified, and then we can write the transfer function in this form f1 omega. First of all, why omega? Because this transfer function will be a function of frequency. Okay, this will be a function of frequency. Let me select the arrow again. So this will be function of frequency, and this transfer function is nothing but the ratio of amplitude of this displacement at Z equal to 0, that is at the ground level, divided by the same amplitude of this displacement when Z equal to H. So this is how this transfer function is defined, and this should be at any time t. But we are interested in the maximum value of U. So U max at any time t. So once you do this, and once you put Z equal to 0 and Z equal to H and B equal to A in our equation, then you simplify, A is cancelled out. Ultimately, you end up 1 over cos kh, where k is nothing but omega or Vs. So f1 omega is this one. So this is basically f1 omega. Okay, so ultimately the value of f1 omega is k. Now this was the case f1 omega. It could be because cos theta omega h or Vs, cos theta could be either positive or negative values. But because we are interested only in this magnitude rather than direction, so let's say this modulus of this transfer function is called the amplification factor, and this is given from this relation, where irrespective of whether cos theta is negative or positive, you have this. But one thing is sure: the value of this the denominator cos theta cannot be more than 1. It could be 0, it could be -1, or it could be +1. But even if it is -1, then it is because you are absolute value, then you have 1. So that means because surface as a result, this value is always less than 1. So that means f1 omega will be always greater than 1. So that means the surface displacement is always at least as large as the bedrock displacement, and at certain frequency is much larger. However, this is the condition when you do not consider the damping in the system. Okay, so if we plot for different value of omega h or Vs, f1 omega, then we got this kind of plot here, where this kh is nothing but omega h or Vs. So I can write it here. This is nothing but this kh is same as k, because your omega k is omega or Vs. So this can be also written as kh is omega h or Vs. So when your this value of kh is pi by 2, then cos pi by 2 is 0, cos 3 pi by 2 is 0, 5 pi by 2 is 0. So where this peak is infinity, going to infinity. And when cos theta equal to 0, this is 1. So this is 1 when cos theta equal to this is 2 pi. So this will be 1 here again, and this is corresponding to pi. Okay, so when theta cos pi equal to -1, cos pi equal to 0, cos 0 will be 1, cos pi will be 1. Yeah, so it will be 1. So this way, and this will be related to this here. This will be related to 2 pi. So again, these are the points where it is. So here, let's summarize it. Thus, f1 omega is the ratio of the free surface motion amplitude to the bedrock motion amplitude, so which we have already discussed. As the value of this factor omega h or Vs approaches pi by 2 plus n pi, the denominator of above equation becomes 0, which implies infinite amplitude. amplification or resonance will occur. This simple model illustrates the response of a soil deposit is highly dependent on the frequency of the base emission. Because in this parameter, omega H or Vs, Vs is fixed for a particular site, H is the thickness of the soil layer is fixed. So as the omega, which is frequency of excitation changing, your this transfer function F1 omega or amplification is changing. So that means in 1D ground response analysis pointing out that as your frequency of excitation varies, your amplification will keep changing. Okay, so this is mainly and this depends on the first of all frequency of base motion, and it also depends on the geometry, that is thickness of the layer on H, and metal property, that is the shear velocity of the soil. Okay, so this is, and one thing is sure here, that in any case the value of F1 omega will be not less than 1, always more than 1. It is 1, then starting going to infinity, and then again coming down, then becomes 1, again going to infinity. So all these things are. So this is variation of steady state response for undamped linear elastic layer. All this case was when you neglect the damping of the system, but that is not the real case, because the soil has some damping, and that is fortunate. If soil will not have any damping, then at the time of at the natural frequency there will be resonance, and the amplitude will go to infinity, and it will cause that lot of destruction. However, we are fortunate that soil has the damping, but the presence of the damping complicates the solution. That instead of F1 omega, now we got F2 omega, and in this case the type of unbounded amplification predicted by NL is not practical, as no dissipation of energy or damping was assumed. So as discussed, since damping is present in all materials, more realistic results can be obtained by repeating the analysis of the damping. So rather than going in the derivation, when the damping is present in the system, and assuming the soil to have the shearing characteristics of Kelvin-Bogart solid, and writing this equation, then F2 omega is given from this relation, where again you could see what is this parameter, damping ratio is introduced. This parameter is nothing but damping ratio of the soil, Chi. Now let's say if there is no damping in the soil, if I put Chi equal to 0, then again the solution is same as earlier. That means this will relate to this term. So that means this solution can be used even when you don't have the damping in the system, simply putting Chi equal to 0. So now let's analyze this equation. And as earlier, we can plot the variation of F2 omega with omega H over Vs, and we can analyze. But before that, for a small damping ratio, above equation indicates that the amplification of damped soil layer also varies with frequency. So first of all, the variation, this will be also a function of frequency as before. The amplification will reach a local maximum whenever kh is pi by 2 plus n pi, but will never reach a value of infinity. Even if because even if this first term is 0, when omega H over Vs equal to pi by 2 or 3 pi by 2, but still due to the presence of the damping, denominator will never be 0, and as a result your F2 omega will have some finite value, not the infinite value as was the case earlier. Okay, and the variation of amplification will factor with frequency shown for different level of damping in the next slide, and you can compare these figures for undamped and show the effect of damping. So this is the result for when you consider damped case. Okay, and what is in this result? Amplification factor with when the value of kh, where kh is nothing but omega H over Vs is varying, and with this varying, and with this case, you can have that what is the result here. So before we go with this, let me relate it to these peak values, where the peaks are coming. So this should be a straight line. So this will be related to pi by 2. And let me erase this one, control option, erase this part and this one as well as this here. Okay, again. So what you have here is going straight. Peak is here. The peaks is this will be related to pi by 2. Okay. Then the second peak, that means 1.57, and this will be related to what is 3 pi by 2. 3 pi by 2. Then next will be related to 5 pi by 2 and so on. So this influence of frequency on steady state response. So first of all, omega n, the natural frequency, where you got these peaks are given by Vs by H pi by 2 plus n pi, where n is 0, 1. So when I put n equal to 0, then it will be Vs pi by 2 H. That means that means omega n, omega s or Vs will be pi by 2. Okay. But one important issue is here. See, earlier when the damping was not present in the system, then all the peaks was infinity. Okay. But when due to the presence of damping, the first peak come very much down, and the second peak is further down, so it is 1/3 of the first peak, then 1/5, and so the effect of damping is much on the influence of the damping is more on high frequency than compared to lower frequency. So the damping's effect is more at higher frequency compared to lower frequency. That is one thing. Second thing, as you increase, this curve is for 5% damping, this is for 10%, 20%. So as you change the damping ratio, then this comes down here. In fact, the values of these peaks depends only on the damping ratio. It doesn't depend on any other thing. So for example, when I substitute in this equation, omega h or Vs equal to pi by 2, this term will be 0. And in the second term, omega h or Vs will be pi by 2 into chi. So you get F2 omega, you will obtain F2 omega simply at the time of resonance. I can simplify for you F2 omega, and that should be done rather than putting all the numbers. F2 omega at the time of peak, for the first peak, let's say we are calculating, it will be simply 1 over chi into pi by 2. Okay, so that means it is inversely proportional to the damping ratio. As you increase the damping ratio, its value will decrease. So simply, these peak values are depending only on the damping ratio. They are not depending on H or Vs. So for example, if you put 5%, then you will get this value. If you put 10%, then it will be half, again 1/3. So this is explained this way. Now continue with that. The greatest amplification factors occurs approximately at the lowest natural frequency, also known as the fundamental frequency, and this frequency will be when n equal to 0 and omega naught will be pi Vs over 2h. And if you convert this into in frequency, this was angular circular frequency. So in terms of then omega over 2 pi. So if you do like this, divided by 2 pi. If I divide it by 2 pi, then what I get here? I get Vs by 4h. So this gives you the first or fundamental frequency of the soil layer, which is inbuilt, which is fixed at the base. If you have a soil layer, so this the frequency, natural frequency or fundamental frequency can be found simply Vs by 4h. Okay. Let me erase this one because it is not visible. Okay. All right. So using this relation, one can find the natural frequency. And you know the time period or period of vibration is opposite of this frequency, so it will be 4h or Vs. So the characteristic time period, which depends only on the VH increase, provide a very useful indication of the period of vibration that can be expected. So this was all about damping. So this is one numerical example here. In this case, what is given the data, I will discuss very briefly. G is given, gamma is given. So first thing, because Vs is not given here, so you need to calculate the value of Vs here in this case. And Vs is, as mentioned earlier, this can be calculated by simply G by rho. If this is the situation comes, so G by rho, and rho, you know that is nothing but gamma by G. So whenever this kind of problem comes, then you need to have taken like this. Okay. So you can work on this. The data is there, and then you will get some questions on this example, or maybe the change data, similar example. Continue with this. Now let's come to introduction of two-dimensional dynamic analysis. The methods of 1D ground response analysis are useful for level or gently sloping sites with parallel material boundaries. Such conditions are not uncommon, and one-dimensional analysis are widely used in geotechnical earthquake practice. That means where you have the level ground or you don't have any sloping ground, then you can use. But there are some problems of interest where you can have a sloping ground, or you may have some other type of structures. Then 1D ground response analysis may not be acceptable, and we need to go for two-dimensional or possibly even three-dimensional analysis. Let's see what are the situations where 2D or 3D analysis is kind of a must. So these are some of the examples of common problems typically analyzed by 2D plane strain dynamic response analysis. When you say plane strain, that means one of the dimensions are very long, and for example, can happen in cantilever retaining walls, and then earth dam, or maybe in a tunnel where one dimension is very long, and then we can apply the plane strain condition, and applying the plane strain condition, a 3D problem can be converted into two-dimensional problem. So the problem shown in this figure can be dealt with the two-dimensional dynamic analysis, but in a very much important projects, one need to go for three-dimensional analysis. Now, whenever we deal with this one-dimensional or two-dimensional analysis, particularly, then one of the in 2D analysis, one of the issue comes is the boundary conditions. That what we will apply on the boundary, because when you consider mass, some dimension of the Earth, then we need to apply some boundary condition. And for computational efficiency, it is desirable to minimize the number of elements in any finite element analysis. Why finite element analysis? For 2D or 3D analysis, we require finite element analysis. 1D analysis, you may go with the layered analysis. You may not require for 1D analysis FEM, but for 2D and 3D, you require finite element analysis. And for computational efficiency, it is desirable to minimize the number of elements in the finite element analysis. And decreasing the number of elements is basically telling, in other words, that let's minimize the size of the discretized region. And if you want to minimize the size of discretized region, the influence of boundary conditions becomes more significant. And let's discuss how we can go for that. For many dynamic response and SSI problems, ridged or near ridge boundaries such as bedrock are located at considerable distance, particularly in the horizontal direction from the region of interest. If you could find a bedrock, then there is no problem. As a result, when wave energy that travels from the region of interest will be effectively removed permanently from that region if you have some bedrock there. So, in a dynamic finite element analysis, it is important to simulate this type of radiation dynamic behavior. And most commonly used boundaries for finite element analysis can be divided into 3 groups. What are the groups? These are shown in the slide. You could have 3 types of finite element mesh boundaries. These are in the first case, the most simple boundary, and it is called elementary boundary. And in fact, this is not a kind of a special boundary. Rather, you are applying some condition, restrictions, and here 0 displacements are specified. For example, for 2D case, if I prescribe this boundary condition, that means because this roller are saying that you can permit the displacement in this direction, but perpendicular direction restricted. Again, in the same case here, in the vertical direction, it is permitted, but in the horizontal direction, it is restricted. So you are applying, putting some restraint for elementary boundary. Then you have some local boundary, which is normally consists of viscous dashpots, where you consider only dashpots, means dampers. Okay. But what is the problem with this first boundary? That it is very simple. It can't be used for important projects. In the second case, for viscous boundary, they are good when your waves are vertically propagated shear waves. But if you have inclined waves, then the viscous boundary is also known. And in that case, if you have inclined wave, then we need to consider what is called lump parameter consistent boundary, which consists of spring, dashpot, and masses. And for consistent boundary, though it is more difficult compared to elementary and local boundary, but they will serve the purpose. And even in this case, if you have inclined waves, then that is also fine. So this was all about boundary condition. Now for the reference for this today's lecture is here. Is in the Kramer's book on geotechnical earthquake engineering, and there is a chapter called ground response analysis. So you can go through that chapter in detail if anyone want to have more detail about that. So with that, thank you very much for your kind attention. And this ground response analysis is the first step of any SSI problem. Important, and that because as we discussed earlier, SSI itself is important for earthquake resistant design of foundations. Thank you very much.